10b detecting, transferring, and storing charges. 10.6 detecting charges. How can you tell whether an object has a positive charge, a negative charge, or no charge at all? Charges can be detected with an instrument called an electroscope, which uses the law of charges. The simple electroscope shown in Figure 10-13 consists of a flask with a one-holed rubber stoppet, two thin leaves of metal foil attached to the bottom end of a metal rod, and a metal sphere attached to the upper end of the rod. The rod passes through the stopper, which acts as both a support and an electrical insulator. The metal rod in the electroscope transfers charges between the sphere and the leaves. If we place a negative charge, extra electrons, on the sphere, the extra electrons instantly repel each other and spread out down the rod to the metal leaves, making both leaves negatively charged. The leaves, being very flimsy compared to the strength of the electrostatic force, are repelled and spread apart as the law of charges predicts, thus indicating that the electroscope is charged. The leaves will stay spread apart until the electroscope is discharged. Touching a positively charged object to a neutral electroscope charges the electroscope by drawing electrons off the metal sphere. The remaining electrons in the metal parts redistribute evenly as they repel each other, leaving a net positive charge throughout. The foil leaves again spread apart as they repel each other, having the same positive charge. These mechanical electroscopes can detect only relatively large charges because tiny electrical charges produce only tiny electrical forces of repulsion, which cannot move the metal leaves much. More sophisticated electroscopes use electronics to measure very small charges. 10.7 transferring charges. Some materials offer little resistance to electron motion. These materials are electrical conductors and are usually metals such as copper, aluminum, silver, and gold. Electrical insulators do not allow electrons to move easily. Glass, wood, and rubber are all insulators. For example, electrical wires are made of conductors. The plastic coating on the outside of electrical wires is an insulator. Most materials are either excellent conductors or excellent insulators. A few materials called semiconductors allow limited electron flow or conduct only under certain conditions. The elements silicon and germanium are examples of natural semiconductors. Scientists and engineers have developed thousands of semiconductor compounds that are used for microelectronic components in the modern computer and integrated circuit industries. Static charges can move when conditions allow them. When objects with different charges touch, some of the electrons transfer from one object to the other. For example, when you walk across the carpet on a dry day and then touch a doorknob, the shock you feel is caused by electrons jumping from you to the doorknob. As mentioned earlier, the loss of static charge as electrons move to another object is called electrical discharge. Static charges can discharge slowly, as when the charge on a comb leaks away, or they can discharge abruptly and dramatically. Lightning is an instantaneous electrical discharge, produced when electrons in the earth or clouds are discharged through the insulating air. See the facet on the following page for a discussion of the formation of terrestrial lightning. 10.8 Using conductors to solve problems. Can you think of something we can use to protect buildings from lightning strikes? During the mid-1700s, Benjamin Franklin began experimenting with electricity. He showed that lightning is electricity, and he believed it could be controlled to some extent like other electrical phenomena. He invented the lightning rod, a device we still use to protect buildings from lightning strikes. Lightning rods are made of conductors that are attached to the highest point of a building. The lightning's electrical current flows through a low-resistance wire to dissipate its charge harmlessly in the ground rather than passing through the building's structure. Lightning rods are often used in cell phone towers, high-tension power lines, and electrical substations. Franklin's invention was widely held to be heretical. Many religious leaders in America and Europe who did not have a proper view of God and science said that lightning was God's tool for punishing disobedient people. To them, the invention of the lightning rod was an attempt to play God. This resistance resulted in even more deaths. In 1767, shortly after the invention of the lightning rod, an Italian church, San Nazaro in Brescia, housing a large stock of gunpowder, was struck by lightning. The building exploded, killing 3,000 people, and the city suffered incredible damage. The Bible-believing Christian understands that God is indeed in control of every lightning strike. However, we do not always know why it strikes where it does. It's foolish to say that it is always for judgment, and it's foolish to claim that humans should not try to tame lightning to avoid God's judgment. Sometimes God uses seemingly bad things to show us His mercy. John 9:1-3, in this case, His mercy through humans' use of science. 10.9 Storing charges. The first scientists to study electricity could not produce enough electrical charge for more than a brief demonstration. After rubbing a rod with a cloth, the accumulated charge soon leaked away. They invented friction machines that could generate stronger sparks, but when the machine stopped, the charge still dissipated immediately. What they needed was a means of storing a large charge. The first solution to the problem was invented independently by Ewald von Kleist, Leyden 1745, and by Peter van Musschenbroek, a few months later in 1746. The device was called the Leyden jar, after Musschenbroek's hometown of Leiden, Netherlands. The early Leyden jar consisted of a large glass jug, coated inside and out with thin layers of lead, leaving the upper end of the jar uncoated. An insulated stopper plugged the jar. A metal rod was inserted through the stopper, which was attached to a metal chain resting on the inner lead coating at the bottom of the jar. The upper end of the rod supported a metal knob or ball. See Figure 10-16. Kleist and Musschenbroek discovered that two layers of a conductive material, separated by an insulator, could store more charge than the conductor alone. The glass, a good insulator, separated the metal layers. When a source of static charge was applied to the metal rod, the charge was transferred through the chain to the inner metal coating. This charge induced an opposite charge on the outer coating, permitting even more charge to be deposited on the inside of the jar. In this way, very large charges could be stored. Kleist and Musschenbroek learned this the hard way when they both unexpectedly received severe shocks while experimenting. Later, scientists learned that if they connected the outer metal coating to a wire stuck into the earth, which became known as an electrical ground, far more charge could be stored in the Leyden jar. The ground acted as a source for new electrons, or a place to receive repelled electrons, whichever tended to increase the induced charge on the outside of the jar. Modern charge storage devices are called capacitors. These compact devices store charge in most electronic circuits. The structure of a capacitor is similar to that of a Leyden jar. A capacitor is basically two layers of metal foil separated by an insulating material and sealed in an insulator. The amount of charge stored in a capacitor depends on the area of the metal foil and the kind of insulator. 10.10 Applications for static electricity. Electrostatic principles help control pollution in some factories. As smoke travels from machinery to the smokestacks, it passes electrodes that charge the smoke particles. Just before the smoke enters the smokestacks, the charged particles are collected on oppositely charged metal plates. Much of the remaining vapor released through the smokestack is harmless steam. Frequently, the particles attracted to the electrodes contain valuable chemical substances that can be recycled. This type of anti-pollution device, called an electrostatic precipitator, substantially reduces certain kinds of air pollution. Perhaps the most familiar application of static charges is the laser printer, a high-speed computer printing technology used everywhere. The heart of the printer is a special drum coated with a semiconductor. The atoms in the drum's surface are given a charge that does not drain away because the surface normally doesn't conduct electricity. It acts as an insulator. If strong light strikes the drum's surface, however, the semiconductor changes to conduct electrons away from the surface. Wherever light falls on the surface, the charge disappears. To print a page, a computer-controlled laser beam paints the document image onto the drum through a series of mirrors and lenses. The printer then charges the toner, a black plastic and carbon powder used to create the image, with the same electrical charge as that on the drum. The toner sticks to the drum by static electrical induction wherever the laser beam has neutralized the charge. The drum then rolls over a sheet of paper, transferring the toner onto its surface. Hot rollers melt the toner onto the paper, completing the print.